Okay, so welcome. This is MEC 2960. We're going to overview hardness testing today and heat treating. As an introduction, we're looking at the Rockwell hardness tester. We have specimens for calibration that are provided by the manufacturer, Rockwell hardness B scale and a Rockwell hardness C scale. Two different indenters, if you will. B, which is a small round sphere, and then we have a diamond tip on the Rockwell C. So what we're going to do is first calibrate. What we'll do is we'll add the hardness tip. This one's a B tip, small diameter ball. And then we'll use the standard. This one calls out a Rockwell hardness B of 95.8. And we can use this to determine whether or not the machine is approximately, accurate, if you will. What we don't want to do is load the sample up in close proximity to a previous test because it's been hardened. What I'll do is I'll go ahead and apply a minor load. And in doing so, I'm forcing the sample up into the indenter. I can then zero the scale, both B and C. We're on the B scale, which is the red. And at this time, what I want to do is I've already preset my major load at 980. And I'll go ahead and apply that load now. So that's going to drop weight and force the material into the indenter. What I'll do is I'll wait for the needle to stabilize, and then I'll take the load back off, and we should be able to read the Rockwell B of approximately 97. I'll unload the sample with the minor load. And this one had a Rockwell B of approximately 95.8 or 96, so we're essentially on. So that's a quick check of the Rockwell B, whether or not this is set up properly. The next thing we'll do is take 1018, and this is a virgin sample, essentially not heat treated. I'll look at the surface. It's already been cleaned to some degree, and we can now load that in here. And again, what I want to do is I have my major load off. I'm going to apply a minor load. Approximately 3 rotations of the dial, which will bring us into the red. I can then zero the dial out. Again, apply my major load. Wait for the needle to stabilize. Remove the major load. And now I can record my Rockwell B of approximately 87. I'll remove the sample, and that takes care of that portion. Okay, so now we've done the preliminary hardness test with the Rockwell B on the 1018 sample. We have a couple samples in here already that have been heat treated for approximately 30 minutes. The temperature is 853 degrees. And when we open the door, I'm going to grab the samples with the tongs, appropriate safety equipment on, and then we're going to drop one sample into water and then another sample into oil. I'm also going to load this 1018 that has not been heat treated, and then that'll be sitting in the oven for approximately 30 minutes. Very hot. And my second, you can see the color on that, into the oil. Then I'll take my 1018. I'll put that in here, and we'll start the clock, and we'll start heat treating that. The temperature should come right back up to approximately 850 degrees. I'll now remove the samples from the water. They'll be cool, but I'll still use the tongs. We'll put them up on the table. Still steaming. If we're still hot. And that concludes the heat treatment demonstration. Okay, so now we're going to do a Brinell hardness test, and this test is done with softer materials. So we have a piece of aluminum, I think it's 6061 T6 perhaps. In doing this, what we want to be aware of is that we have control on the force that's being applied in kilograms. I can turn the air regulator on, which I've already done. So I have a pneumatic piston. I bring that up to 500 kilograms approximately, and I back the anvil off because I don't want to drive the load nose into the anvil itself, which is made out of steel. I know that the stroke on the piston is approximately maybe 1.5 inches. So that's the furthest travel. Now I know that I can safely bring my sample up on the anvil and then back off the piston, if you will. Before I do the test, I want to determine carefully, when you put your hands in here, you should have the load backed off. I remove the ball for this Brinell hardness test, and I measure approximately 0.393 inches in diameter. I then can put the ball back in there. And now I load that load nose, steel ball, verify that I'm at the 500 kilograms set point, and now I'll bring the sample of aluminum in close proximity to the load nose. And I can just touch that off. And when I open this valve here, then that's going to apply that force. I'll then remove that. Back the sample down. And I'm going to record the diameter of this indentation. What I noted when I just did the test is that when I applied the load, pulling the piston out again, it's actually above 500, so I'm going to back the regulator off and redo this test. Piston back in. So diameter 2 for the second test may be slightly different than that first one. And I'm going to do 3, statistically speaking, so that gives me some more meaningful data perhaps. Applied the load. Looks like I have 500 kilograms of force. And then I can remove that load and then back the sample down. So for test 3, I have another indentation that we're going to measure the diameter on in a moment. I'm going to turn the regulator off. Back the anvil down. All right, so now I need to go ahead and measure the diameter of the indentation. I'm going to use vernier calipers to do that. There's a number of ways to do it. Optically might be a better way. I want to zero the dial indicator, make sure I'm at 0. And then essentially, I'm going to open up the dial indicator to span the diameter of the indentation. And it appears I have approximately 0.11. I can look at the second indentation. And again, it's approximately the same thing, 0.11 inches. And lastly, roughly the same measurement of the diameter, 0.11. Okay, so what we've done is the hardness test, Brinell on the aluminum, 6061. So I'm going to go ahead and just do a quick test on that to see what I get for results on the Rockwell hardness tester. I'm all set up. I have my ball indenter, and I'm on a major load of 980. So what I'll do is I'll carefully preload with a minor load. Zero that out, apply the major load, wait for it to come to stabilize, if you will, and I'll pull that off, And if I read this correctly, I'm looking at a Rockwell B of approximately 51. Okay, while I have the Rockwell B set up on the hardness tester, I have my oil quenched sample. That was the 1018 that we heat treated already for approximately 30 minutes at 850 some odd degrees. Same thing, what I want to do is go ahead and apply minor load. Applying the major load. Wait for it to stabilize, and then remove the major load. And this appears to be a Rockwell B of approximately, where am I at? 82. Yeah, 82. All right, so I'm going to take that minor load off, and what I want to do is go to another side of the sample. And the sample has been cleaned already, just to get another number. Apply my major load. Wait for it to stabilize. Remove that, and I'm sitting on a Rockwell B of approximately 82. So now what we're going to do is swap to our other sample. However, as an experimentalist, to verify that nothing's changed, I'm going to actually go ahead and put the standard back in there. And this calls out a 95.8 Rockwell Hardness B, and tells me whether or not anything's changed during the test. All those recording here today are hoping that we get that same number approximately. Apply the major load. Stabilized. Remove the major load. And we're at approximately a 98 Rockwell B. So essentially, we're repeatable. The system hasn't changed. I'm going to now remove the indenter with the small diameter ball for the Rockwell B hardness test, and we will add in the diamond tip. This is for Rockwell C. So we're looking at measuring the heat treated hardness, and this one is actually, where's my sample? Oh, very good. Thank you, George. All right, so this is water quenched. Correct? All right, good. So again, my 1018 is water quenched. I'm on now a Rockwell C scale, so I have to change my major load to 1471. I'm going to go ahead and verify the machine is accurate to some degree. I've got a standard sample of 47.7 Rockwell Hardness C. I'll look for a non-used region of that. And again, zero that out, apply my major load. Remove that. And wonderful, Rockwell C of approximately 46, so I'm within 1.7 as one quick measurement. Now I can take my quenched 1018 and test that on the Rockwell C scale. Minor load is applied, apply my major load, remove the major load, and I'm on a Rockwell C of approximately 41.5. As an experimentalist, what you want to do, statistically speaking, is obviously take a couple samples just to see if it's repeatable, or if there's regions that had a heat treatment to them that then is different from another region on that same sample. So I zero it out again, apply my major load, remove that, and I do see here that I have a potentially bad reading, Rockwell C of 11. I'm going to go ahead and do one more test, and I'm actually going to take a closer look at what's going on there. So I'm going to zero that out, minor load, apply the major load. So this one's giving me a Rockwell C of approximately 32. So what I want to do finally is, observe where I took the sample, how the sample was post-processed, and why I may have deviations in those numbers. But again, I'm going to quickly check the machine with a standard. Oops. Apply the major load. And I'm at a Rockwell of approximately 50 on a C scale. Again, I'm off by a couple points on a Rockwell Hardness C. So that tells me that the machine is on, and I would have deviations in the hardness along maybe the length or on different sides, depending upon how it was actually heat treated and quenched. That concludes that portion. All right, so next what I want to do is, am I looking at a 1045? All right, so the 1045 has already been heat treated to approximately the same temperature that was recorded previously. I'm looking at the surface of it, and it's been prepared pretty well. What I want to do is go ahead and do the same thing, and I'm going to apply the minor load. Major load, remove the major load. Again, Rockwell C of approximately 85. And that's the 1045 heat treated, quenched in, or not, oil or water? No quench, sorry. 1045, air cooled?
Slow air cool.
Slow air cooling. All right, very good. All right, so I'm going to take one more sample on this 1045 heat treated and slow air cooled, if that's correct. Probably going to see a deviation in that result. Rockwell C of approximately 76. So again, as an experimentalist, you would want to go ahead and take a number of samples that gives you a couple data points, and then you can make some conclusions based on that.